So chapter 4, as promised, is really big, and here is the next portion of chapter 4, which is called solution concentrations. And in this one we will learn about how to make solutions of a specific concentration. Concentration is given in molarity, so which is moles per liter. Okay, and so how to make a 2 molar solution or 3 molar solution, and then how to make it if you already have a solution made. So if you have a 16 molar solution, then how do you make it to be a 3 molar solution, which is called dilution. So we'll talk about two different things here: making a solution from a solid versus diluting a solution. So those are the two things covered in this little portion. So in the concentration of solutions, we try to find out how much of a solute is in a solvent. Uh, Solutions, if you remember again, are solute in a solvent, and solute is a smaller quantity and the solvent is the larger quantity. So you have to know the quantities of both in order to know the concentrations. Concentrations are measured in different ways. There are percent solutions, molarity, and molality. Okay, you will do a great detail of all of this in Gen Chem 2. Right now we're going to do only molarity, okay, but I will introduce all the concepts to you so that you understand them and you know when you see the solutions as to what they mean. So in percent solutions we have mass by mass percent, in which you have grams of solute and grams of solution times 100%. Mass by volume percent is gram of solute and milliliters of solution. Volume by volume is milliliters of solute and milliliters of solution. Again, all of these are in percent quantities. Depending on what kind of solute and solvent you have, you make the percent solutions accordingly. So for example, if you have two liquids that you want to dissolve, then you might be better off doing a milliliter by milliliter, okay, percent solution. If you have salt, for example, NaCl that you're trying to dissolve in water, then you can do mass by mass. So you can have grams of the NaCl. You can also have grams of the water that you're trying to dissolve, or you can have milliliters of the water that you're trying to dissolve. So depending on what kind of solution you're making, you take the quantities accordingly. I want to point out one thing for you so that you don't forget this. Over here, when you read this formula, it says grams of solute over grams of solution. Okay, so solution meaning that this is solute plus solvent. Okay, so for example, if you have 2 grams of solute in there, then the gram of solution is total, which is 100. Okay, remember this is percent. So which means your solvent is actually only 98%. All right. So you have to remember that part. Gram of solute and milliliter of solution is a little bit different, because in gram of solute and milliliters of solution, these things are considered to be additive. Okay, which means that if you add 2 grams of solute to 100 grams of or 100 milliliters of water, it does not change the volume of the water. Okay, so even though the milliliters of water that you're taking is 100 milliliters, because it's a 100% solution that you want to make, or in 100 quantity, but still it's not 98 milliliters, okay, because these quantities are considered to be additive. All right, volume by volume is a little bit different, because in this case both the things are non-additive. Okay, so for example, if you want to make a 5% solution of, say, isopropyl alcohol, then you would have 5 milliliters of the isopropyl alcohol, and you would have 95 milliliters of water, okay, in there. So that's how these quantities are made, and this is how we make them in the lab also. Okay, it's nothing mysterious about this. When you see percent solutions in your lab benches, this is how we make them. Molarity is what we're going to use a lot in chemistry, and that is moles per liters of solution, not milliliters now, liters, okay, and again of solution. And moles for us, of course, is a big thing, because moles gives us the number of atoms that we have, or molecules that we have in a certain amount. So we will talk more about molarity in this chapter. And molality is moles over kilograms of solution. This is used a lot more in biology than it's used in chemistry, okay? But you will learn all of these concentration calculations in Gen Chem 2. Here, we'll talk only about molarity. So then let's talk about molarity, okay, which is the molar concentration. And molarity is given by capital M. And molarity is moles of solute divided by liters of solution, and the way we say it is moles per liter, or this is the molarity, okay, of the solution. Um, in order to make solutions in the lab, you still have to convert the moles to grams. Remember, you cannot weigh out moles, so you still have to convert them into grams to make the solution, all right? Depending on how much you're making, that's the amount of volume you will need. And of course, the grams, okay, that you will need. So when we say that we have 3 molar solution of NaCl, it means that in 1 liter of solution, we have 3 moles of NaCl. In 3 molar solution of H2SO4, we have 3 molar or 3 moles of H2SO4 in 1 liter. Okay, and that's 3 moles. And remember, you have to find the grams of that. So that's how it works out. If you have a smaller quantity of HCl or NaCl, 200 milliliters of 2 molar HCl, so it means that the moles in that quantity are going to be smaller, okay, because you're dealing with only 200 milliliter. In 1000 milliliters, okay, there are 2 molar. So in 200 milliliters, it should be 1/5, okay, of that amount. So when you try to make the solution for only 200 milliliters, then you will have to calculate 1/5 of the grams, okay, of 2 molar. So anyway, we will do some calculations in a little bit, but here this little figure here represents how we actually make these solutions. And this is first done by weighing the amount of substance that you need, which is a solute. And remember, the solute can be a solid or it can be a liquid also. It doesn't matter, so long it is the right number of moles. Okay, then you weigh that amount, you add that to a volumetric flask, and then you make it up. You make up the solution until the mark, okay, where it is graduated. And you've used a volumetric cylinder before, so you know how to make these solutions. So let's work on a couple problems for molarity. The first one is a straightforward one. If you place 1.52 grams of potassium dichromate in a 50 milliliter volumetric flask, and then you add water, okay, enough to bring it to the neck of the flask, then what is the molarity of potassium dichromate? So you already have 50 milliliters of water in there, which you will convert to liters. And then you have grams of potassium dichromate given to you, which you will convert to moles. To find the moles of potassium dichromate, you need to find the molecular mass, or the formula mass of potassium dichromate, which is 294, 2 potassium plus 2 chromate plus 7 oxygen. Okay, remember that's how we do it. And then you go ahead and plug it in the formula. Here, this is the calculation of moles. So we're just trying to do everything in one step, okay, over here. So 1.52 divided by 294 grams. And this gives you the moles of potassium dichromate. You divide the moles by the liters, okay, of the solution, which is 50 milliliters. So you convert that into liters by multiplying it by 10 to the negative 3. And then you get the molarity, okay, of the solution. So what this means is that if you have 1.52 grams of potassium dichromate in 50 milliliters of solution, the molarity of that solution is 0.103 molar. Okay, that's what this means. So it's a nice straightforward calculation. The next calculation we have is a solution of sodium chloride used for intravenous transfusion has a concentration of 0.154 molar NaCl. How many moles of NaCl are in 500 milliliters of the saline solution? And then how many grams are also in that solution? Okay, so you're supposed to calculate the moles and also the grams. In the first case, the first problem that we solved, we actually had grams given to us and the volume given to us, and we were supposed to calculate molarity. Now we are given molarity and we are going to be calculating grams. Okay, so we're doing reverse of what we started with, okay, in the first problem. So our formula still is the same, which is molarity is moles over liter. So to find the moles, okay, of the solution, you will do the cross multiplication, which is molarity times liter. And so the molarity is 0.154 and the volume is 0.5 liters. Remember, this is in milliliters, so you have to convert it into liters, okay, because of the units. You need to be consistent. And so this multiplication gives us 0.0770 moles of NaCl. So this is part of our problem, and then the second part of the problem is converting that into grams of sodium chloride. And so here we go. Take the molar mass of sodium chloride, which is 58.4, and you multiply the number of moles, okay, by that grams, and you get 4.50 grams. It means that if you have 500 milliliters of a 0.154 molar NaCl, you have 4.5 grams of NaCl. On the other part of this problem, if you flip it and you think about it, you would need 4.50 grams of sodium chloride and dissolve it in 500 milliliters of water to get 0.154 molar solution of NaCl. Okay, so these are a couple calculations for calculating molarity and vice versa. So here is another calculation then. Calculate molarity of a solution prepared by dissolving 45 grams of potassium iodide into a total volume of 500. This setup over here is slightly different from what I showed you before. And I thought that we'll just try and do it in two different ways, and you can choose whichever way suits you. It doesn't matter to me. This is more like the dimensional analysis, and the first one that we did was more like a ratio method, okay, and like using the formula. So here we have 45 grams, okay, of Ki in 500 milliliters of solution. Okay, so you take those two quantities. Now remember, our units are moles per liter. That's what we are going, okay, with the final answer, because that's what we have to calculate, the molarity. So our final answer should be moles per liter. So we have to convert grams into moles and milliliters into liters. Okay, and the liters will be down here, not up there, okay, because it's moles per liter. So start with 45 grams of Ki, convert that into moles. You have 500 milliliters of solution. You convert that into liters, and here's your molarity. So you can do it this way also, all right? You can take it step by step if you want to, okay, which means you can calculate the moles first using Ki and the molar mass of Ki, and then you can do the conversion of the milliliters to liters, okay, in the second step, however you want to do. Okay, so here is another type of problem. How many milliliters of 3.5 molar solution can be prepared from 75 grams of the solid? Okay, so now you are trying to find the volume. We've tried to find the mass from molarity. We found the molarity. And now we're actually trying to go for volume. So we've kind of doing all sorts of calculations over here. So the molarity is given to us in this problem, which is 3.5, and we have the volume given to us. Okay, remember we are going to the grams of solution. So you start from the grams, all right, of solution, grams of the. Let's look at another concept of solutions, and that is dilution. So in case of dilution, what we do is we take a higher concentration solution and make a less concentrated solution, which means that we add water, okay, to the more concentrated solution. The important thing over here is that the number of moles of the solute remain the same. Okay, so here is an example of dilution going on. So you have a concentrated solution with a certain amount of volume of solvent and certain quantity of the solute. If you double the amount of water in it, the number of solute does not change. Only the amount of water has changed, but the solute remains the same. So if the solute remains the same, the number of moles are the same. The only thing that has changed is the concentration, okay, because the concentration involves volume of the solvent. The moles, however, will be the same, okay? So the moles in the initial and the moles in the final concentration are the same. All right, the only thing that has changed is molarity. So here when we look at the formula for calculating dilutions is that we have initial molarity times initial volume, which really is moles. Okay, remember we just did that. and then that is going to be equal to the final molarity and the final volume. Okay, so this is initial moles and this is final moles, and this should be the same because the number of moles has not changed, okay, when we did this dilution. A little bit about the practical aspect of making diluted solutions is that you take the concentrated solution, you add whatever quantity you need to a volumetric flask, and then you add water up to the mark, okay, that you need. So if you need to make, say, 250 milliliters of a diluted solution and you have to start with 50, then you just go ahead and add 50 over here in the volumetric flask of the concentrated solution, and you make it up to 250. You don't have to measure how much water you're adding anymore because the volumetric flask already has that mark on it. Okay, so you can see that this volumetric flask is a very useful tool in labs. So here are a couple calculations that we can do for dilutions. The first calculation here is a saturated stock solution of sodium chloride is 6 molar. How much of this solution is needed to prepare 1 liter of physiological saline solution, which is 0.154 molar. Okay, so we are going from a 6 molar higher concentration solution to a lower. Remember, you cannot go from a lower to a higher by dilution because you're adding solvent. Okay, so you can't do reverse. You can only do dilution. So here is how this is done. You set up your initial and final, okay, which is the moles. You try to find out what is it that you're looking for, okay. Usually your initials are the concentrated ones, finals are the dilute. Honestly, it doesn't matter what you do because the most important thing is that you keep your numbers together. Whether you keep the dilute here and the concentrated here or vice versa, it doesn't matter. Okay, you just have to make sure that you keep the quantities together. Okay, whatever it is. So which means that you need to find out the volume of 6 molar sodium chloride solution. So you want to make sure that the molarity of 6 molar and the volume of the 6 molar stay together, and the 1 liter volume and the 0.15 molar stay together. Okay, so that's the most important thing. So here, in any case, our initial is our concentrated solution. So we know the molarity of the initial solution, which is 6 molar. So we need to find out how much volume we need. So you do the cross multiplication. So MF and VF, which is the final moles that you will get, divided by M1, which is the initial, okay, the more concentrated one. You plug in all your numbers in here. So 0.154 times the 1 liter, which is how much you need, okay. So that's the final concentrations and final volume divided by the initial concentration. So you need 0.0257 liters or 25.7 milliliters. So what does this mean now for us? It means that you need to take 25.7 milliliters of the 6 molar NaCl, you add that to the volumetric flask, and then you make it up to 1 liter. You don't have to calculate how much water you're adding. You just make it up to the 1 liter mark, okay, in there. Here's another problem similar to that. For an experiment, the class will need 250 milliliters of 0.1 molar copper 2 chloride, and there is a bottle of 2 molar, okay, copper chloride. So how would you make the 0.1 molar solution? Okay, so which means again you need to find out how much of the 2 molar solution you need. Again, it's a volume thing. So here's another way of setting this up, okay, is that you have the concentrated solution, which is 2 molar, and you're asked to find out how much of volume you would need. So this is the volume of the concentrated, and then the diluted solution you need is 250 milliliters, and the molarity is 0.1 molar of this. So we'll use the MC and the D, and you can use this if you prefer to. So MC is the concentrated molarity, volume C is the concentrated volume, and then D is for the dilutions, okay? And then you go ahead and plug in your numbers. So the molarity for the concentrated is 2, volume we're trying to find out, and then molarity of the diluted is 0.1 that we need, and the volume that we need is 250 milliliters, okay? So if you notice in this case, we did not change the milliliters to liters, and this is because we're doing a dilution. So when you cross out your units, your molarity will cross out with molarity and your units for volume will be left in milliliters. So we are okay with this. In the case of molar concentrations calculation, you do have to convert the milliliters into liters. And if it is bothering you, then go ahead and convert this into liters. Okay, it doesn't matter. By the time you finish doing the calculations, you will have to come down to milliliters again. And remember, the calculation here is 0.1 molar times 250 divided by 2 molar. Okay, so the moles, the molar and the molar cancel out. You're left with milliliters. So what this means is you need 12.5 milliliters of the concentrated copper 2 chloride. And again, you add enough distilled water, okay, to make the 250 milliliters of the solution. That's how we do dilutions. Here are your keywords for this chapter. This is what you should know by the end of this is the solution, the concept of solution, which is a solute and a solvent. Then the only concentration that we focused on was molarity, which is moles over liter. So how do you make a solution of a particular molarity using grams of any substance? And then of course we focused on dilutions, which is taking a concentrated solution and then diluting it. Remember, you cannot go the other way. Okay, you cannot take a diluted and make it concentrated. It's a little bit harder to do. So we do dilutions, okay, for that. So this is what you should know from this portion.